So for section 9.2, we're still going to be looking at our sequences, but we're going to look at what's called monotone sequences. So we took a look in section 9.1 about knowing whether or not a sequence converges. So a lot of situations we want to know, and it's important to know whether the sequence is converging, but the value of limit is not necessary to the problem. So in the last section we focused on finding what the actual limit is. A lot of times they just want to know the convergence or divergence of a sequence. So the first thing we have to determine whether a sequence converges or not is we have to know whether or not the sequence is increasing, decreasing, or strictly increasing or strictly decreasing. So if you have a sequence where your terms are starting with the smallest term and increasing, we say that it is strictly increasing. So for example, if you had a sequence 1, 3, 5, 7, 9, so on. Now the difference between strictly increasing and strictly decreasing is the fact that there are times in the sequence where it may not be that the terms are all increasing. So for example, and this would have to be shown graphically, really like a step function or a piecewise function, if you had the terms 1, 1, 3, 3, 7, 7. So it's increasing, however, there are moments where the terms are not increasing, but their two terms could be equal to one another. Strictly decreasing is when you have terms that are in descending order. So for example, 11, 9, 7, and so on. And then decreasing, just like the increasing, you could have terms that are equal to one another. So like I said, the strictly increasing, none of the terms would be equal to one another. To be just decreasing, you could have terms that are equal to one another. So we could say that a sequence is either increasing or decreasing is said to be what we call monotone. So if we say that a sequence is either increasing or decreasing, it's a monotone. And if it's strictly increasing or strictly decreasing, it's said to be called a strictly monotone sequence. So if you take a look graphically at the sequence n over n plus 1 as n is going to infinity, we would say that this is strictly increasing. Notice none of the terms are equal to one another, and they are increasing. As your n values are increasing, the value of the terms are also increasing. If you look at your sequence 1 over n, this is what we call strictly decreasing. Notice your terms, as n is approaching infinity, the value of terms are getting smaller and smaller. So now if you take a look at this sequence, this is just going to be an increasing sequence. Notice the terms are getting larger, but there are places where the values of the terms are equal to one another. Here, notice your terms are starting off with a larger term and they're decreasing, but we do have values where the terms are equal to one another, so we call that just a decreasing sequence. And then if we have an alternating sequence, the negative 1 to the n plus 1 over 1 over n, this is neither increasing or decreasing. Because if you notice, these terms are increasing, however you have some terms in the sequence that are decreasing. So it's not necessarily that all sequences will definitely be strictly increasing or strictly decreasing, or increasing or decreasing. Now there are tests that we can use on sequences to test to see if it is increasing or decreasing. So these are our tests for monoticity. Monotosity, I should say. And again, what this is checking for is checking for the increasing and decreasing sequence. So determine if a sequence is increasing or decreasing. Monotone, write out the first terms and calculate the common ratio or common difference. And this is the way the table provides a way of doing this. So you have your difference test, you also have your ratio test. So notice what we're going to do, if we take our a sub n plus 1 and subtract it from a sub n and it's greater than 0, then we know that it is strictly increasing. If you take a sub n plus 1 minus a sub 1 and it's less than 0, it's strictly decreasing. If we end up with a sub n plus 1 over minus a sub n greater than or equal to 0, that's where it's increasing. Or less than or equal to 0 is decreasing. So the difference between being strictly increasing versus increasing is that increasing is going to be equal to 0. Strictly increasing must be greater than 0. So that's your difference test. The ratio test, you make a ratio of a sub n plus 1 divided by a sub 1. You're not doing a comparison to 0, you're making a comparison to 1. So if it's greater than 1, it's strictly increasing. Less than 1, it's strictly decreasing. So to practice using our difference, so use the difference, a sub n plus 1 minus a sub n, show that the giving sequence is strictly increasing or strictly decreasing. You're always going to have to state the restrictions on n. So remember, we're looking at sequences that are going to infinity. So some of these terms may start out not being increasing or decreasing, however, and it could change. There's a place in the sequence where it changes from decreasing to increasing or vice versa. So the restrictions on n is where does the sequence become strictly increasing or decreasing. So we're going to do the difference. Again, the difference is we're going to take a sub n plus 1, subtract a sub n from it, and we're checking to see if it's greater than 0. So my a sub n is just my explicit formula of the sequence. A sub n plus 1 you find by adding 1 to n in the formula. So n plus 1 over 4 times n plus 1 minus 1. So then I can simplify the denominator to n plus 1 in the numerator over 4n plus 4 minus 1 is a plus 3. So now I want to check to a sub n plus 1 minus a sub n. So a sub n plus 1 is n plus 1 over 4n plus 3 minus a sub n, which is n, over 4n minus 1. So you do want to condense this to a single fraction, so we do need to get a common denominator. So I'll have to multiply this fraction by a 4n minus 1, the numerator and denominator, this one by a 4n plus 3 over 4n plus 3. So my denominator will be 4n plus 3 times 4n minus 1. So then this numerator, when I know to FOIL out n plus 1 times 4n minus 1, that's going to give me a 4n squared. So my outer and inner terms will be a minus n plus 4n, so that's going to be a plus 3n, and then a minus 1. And when I distribute a negative n, that's going to give me a minus 4n squared minus 3n. So when I simplify this, the 4n squares cancel out the 3n squares. That leaves me with a negative 1 over 4n plus 3 times 4n minus 1. So now when you look at this fraction, the question is, are all of these terms or all the value going to be greater than 0 or less than 0? Remember, you're starting by plugging in 1 for n. Well, if you plug 1 in for n, no matter what, this denominator is going to be positive. So I plug in 1 for n, 2 for n, 3 for n, 4 n, 5 for n, or 100. This denominator is always going to be positive because n is always positive. The numerator, however, is negative. So I know that no matter what, these terms are going to have to be less than 0. So I know it's going to be strictly decreasing. And again, it's going to start being decreasing when n is greater than or equal to 1. Because again, this can't be equal to 0 because even if I plug in, I have to start it with 1 for n. So no matter what, I will not get this fraction to be equal to 0. So it's going to be strictly decreasing, starting with n is greater than or equal to 1. So if I look at another one, 1 minus 1 over n. A sub n is 1 minus 1 over n. Or I can condense this to a single fraction to be n minus 1 over n. So then my a sub n plus 1 is going to be equal to, and again, I'm going to use this one to plug in my add 1 to n. So I have n plus 1 minus 1 over n plus 1. So that leaves me with n over n plus 1. So now again, to use my difference to check for monotosity, I have to take my a sub n plus 1 and subtract a sub n from it. So I have n over n plus 1 minus n minus 1 over n. Again, I need to get a common denominator, which is going to be my n times n plus 1. So I have to multiply my first fraction by an n. So that gives me an n squared. I have to multiply my second fraction by an n plus 1 over n plus 1. So that's my conjugate. So again, that's going to give me n squared minus 1, but don't forget to distribute your subtraction sign. That's going to give me a minus n squared, and then minus 1 with a negative sign in front of it is going to become a plus 1. So again, my n squares will cancel out, and I'm left with 1. So I have 1 over n times n plus 1. So now remember to check to see if this is going to be greater than 0 or less than 0. Again, when I plug in 1, no matter what, this denominator is going to be a positive number. It's going to be greater than 0. So the numerator is always a positive 1, so I know that this is going to be greater than 0, starting with my n value of 1. So 1, 2, 3, 4, 5, etc. No matter what value I plug in for n, starting with n is equal to 1, I know this denominator will be positive. So this is going to be strictly increasing, starting with my terms n is greater than or equal to 1. So that's how you can use your difference test to check to see whether or not you have a strictly increasing versus strictly decreasing sequence. So now remember, with the difference, you're doing a comparison to 0. When you do the ratio test, you're doing a comparison to 1. So we're going to use the ratio to show whether the given sequence is strictly increasing or strictly decreasing. And again, you're going to state the restrictions on n. So now, just another thing about the ratio. You use the ratio if there's no, again, I'm giving you examples of when to use it, but if I just ask you to show it's strictly increasing or it's strictly decreasing, the ratio is helpful when you have factorials or exponential functions in the sequence formula. So given a choice, which one to use when, if you have factorials or the variables in the exponent, it's probably a good idea to try the ratio test first. So again, my a sub n is 2 to the n over 1 plus 2 to the n. My a sub n plus 1 is equal to 2 to the n plus 1 over 1 plus 2 to the n plus 1. So the way my ratio test works is I'm going to take a sub n plus 1 and divide it by my a sub n. Remember, when you divide, you actually end up multiplying by the reciprocal. So a sub n plus 1 is going to give me this 2 to the n plus 1 over 1 plus 2 to the n plus 1. I'm dividing by a sub 1, which means I'm going to multiply by the reciprocal of a sub n. So that's 1 plus 2 to the n over 2 to the n. Now, in order to simplify this, when you see, again, going back to the last unit, remember, when you see an addition sign in the exponent, you can break that up using your properties of exponents. So I can rewrite that 2 to the n plus 1 in the numerator as a 2 to the n times a 2 to the first over 1 plus 2 to the n times 2 to the first times 1 plus 2 to the n over 2 to the n. So I can cross cancel those 2 to the n's. So I'm left with a 2 times 1 plus 2 to the n all over 1 plus 2 times 2 to the n. And again, remember, I'm doing a comparison of greater than 1 or less than 1. So again, you're starting with an n value of 1. So when I plug in a 1 for n, this is going to give me a 3 times 2, which is a 6. This is 4 plus 1, which is 5. So 6 over 5, I know is going to be greater than 1. If I plug in 2, 3, 4, 5, this is going to be greater than 1. So I know this is going to be strictly increasing. For my n values greater than or equal to 1. So looking at B, you have 10 to the n over the quantity 2n factorial. So again, using my ratio test, a sub n is equal to 10 to the n over 2n factorial. So a sub n plus 1 is going to be equal to 10 to the n plus 1 over 2 times n plus 1 factorial, which is actually equal to 10 to the n plus 1 over the quantity 2n plus 2 factorial. So now using your ratio test, I take a sub n plus 1 and divide it by a sub n. So now my a sub n plus 1 is, again, I'm just going to rewrite that as a 10 to the first times a 10 to the nth, breaking up this exponent here, all over 2n plus 2 factorial. I'm dividing by a sub n, which means I'm going to multiply by the reciprocal. So that's the quantity of 2n factorial over 10 to the n. Now you have to simplify your factorials. If you remember the way, and again, I know I can cross-cancel the 10 to the n. Remember, the way you simplify your factorials is you want to take your larger factorial and break it down into the smaller factorial. So I can rewrite this as 10 to the first times 2n factorial over, remember, a factorial is taking a number and multiplying it by its preceding number. So I can break this up as a product as 2n plus 2 times 2n plus 1 times 2n factorial. So this is equivalent to 2n plus 2 factorial. So now what I can do is cancel out those factorials. So I'm left with 10 over 2n plus 2 times 2n plus 1. So now again, I need to compare this to 1. Is this number greater than 1 or less than 1? Again, I'm starting with 1. So I plug in 1 for n. I know 2 plus 2 is 4 times 2 plus 1 is 3. So 4 times 3 is 12. So I know 10 over 12 is going to be less than 1. Again, if I plug in 2, 2 times 2 is 4, 4 plus 2 is 6, times 5, which gives me 30. So even as n is increasing, this denominator is going to be larger than 10. So I know that this is going to be less than 1. So I know it's going to be strictly decreasing for your n values less than, or n values greater than or equal to 1. So that is how the ratio and your difference test works. There's another test that you can use to check for being monotonic, and that is your test for derivatives. You can use your derivative test. So the way your derivative, obviously you're going to find the derivative of the sequence. So you're going to check to see if f prime of x is greater than 0. If it's greater than 0, it's strictly increasing. F prime of x is less than 0, it's strictly decreasing. If f prime of x is greater than or equal to 0, it is increasing. If f prime of x is less than or equal to 0, it's decreasing. This has a similar comparison. I remember it as the D's, the difference test, and your derivative test. You do your comparison to 0. The ratio is the one where you're doing your comparison to 1. So we're going to use differentiation to show that this given sequence is strictly increasing or strictly decreasing, and again, we're stating the restrictions on n. So again, if I know my f of x is equal to the inverse tangent of x, then f prime of x, again, remember the derivative of tangent, inverse tangent, is going to be 1 over 1 plus x squared. So then again, I need to know if 1 over 1 plus n squared, again, I'm doing the comparison to 0. Is this going to be greater than 0, or is it going to be less than 0? Well, if I plug in 1 for n, 1/2, this is always going to be greater than 0. So this is going to be strictly increasing, starting with your terms where n is greater than or equal to 1. So the next one is natural log of n plus 2 divided by n plus 2. So again, my f of x is the natural log of x plus 2 over x plus 2. So yes, you are going to have to use your quotient rule. in order to find the derivative of this. So remember your fig-figgy, f prime g minus f g prime, square the bottom, and away you go. So the derivative of the numerator is 1 over x plus 2 times the denominator, which is x plus 2, minus the numerator times the derivative of the denominator, which is just a 1, over the denominator squared. So this is going to leave me with a 1 minus the natural log of x plus 2 all over x plus 2 squared. So again, I'm looking at the sequence of 1 minus the natural log of n plus 2 over n plus 2 squared. So again, remember, I'm doing my comparison to 0 when I'm doing the derivative test. So the question is, no matter what, I know the denominator is going to be positive because I'm squaring it. No matter what n value, I know this denominator will always be positive. The question is, what's happening with this particular numerator? So here's a 1 minus the natural log of n plus 2. So if I plug in a 1 for n, the natural log of 3 is greater than 1. So a natural log of 4, 5, 6, 7, etc. This value is always going to be less than 0. So I know that this fraction is going to have to be less than 0 because this numerator will be always negative when we plug in 1 for n. So this is going to be strictly decreasing. When n is greater than or equal to 1. So now let's take a look at example 4. So we've done an example using all 3 tests. Now it's going to be up to you to decide which test you want to use. Show that the given sequence is eventually strictly increasing or strictly decreasing. So I have n factorial divided by 3 to the n. So like I mentioned, when you see factorials and exponential, use your ratio to check for strictly increasing or strictly decreasing. And remember, you do a comparison to 1 for the ratio. So your a sub n is n factorial over 3 to the n. A sub n plus 1 is equal to n plus 1 factorial over 3 to the n plus 1. So the way your ratio test, remember you're going to take your a sub n plus 1 and divide it by a sub n. So a sub n plus 1 is my n plus 1 factorial divided by 3 to the n. I'm just going to rewrite that as 3 to the first. Divided by my a sub n, which means I'm going to multiply by the reciprocal of a sub n, which is 3 to the n, over n factorial. So I know I can cross out that 3 to the n. I do need to simplify the factorial, so I need to take n plus 1, which is a larger factorial, and break it down until I get to n factorial. So n plus 1 times n factorial over 3 times n factorial. So I can cross out my n factorials. This is going to leave me with n plus 1 over 3. So now this is one where you have to be careful, because if you plug in 1, again, you're doing a comparison to 1. When n is equal to 1, 1 plus 1 is 2, and this is 2 over 3, which is less than 1. But if I plug in a 2, 2 plus 1 is 3 divided by 3. 4 plus 1 over 3 gives me 5/3, and so on. So this is where I said what started off as being a decreasing changes to an increasing. It's eventually going to become strictly increasing. So I know that at n is equal to 2, it is going to be equal to 1. So this is going to be greater than 1. So I'm going to be strictly strictly increasing. So at n is equal to 2, that's where it's going to be equal to 1. So any of your n values greater than or equal to 3, that's where this is going to become strictly increasing. Because again, what starts out in the beginning we don't care about. We're concerned about what's happening as the n values are approaching infinity. So I know for your n values greater than or equal to 3, it's always going to be greater than 1. So here is my n to the 5th e to the negative n. Again, you have a choice of the test you want to use. This is where I'll probably use my derivative. So again, this is where I do my comparison, remember, to 0. So f of x is equal to x to the fifth times e to the negative x. Again, you can use your quotient rule, or you could use your product rule on this. That's completely up to you, because you could write this as x to the fifth over e to the x. So I'm just going to go ahead and leave it as my product. So f prime of x is my f prime, so that's going to give me a 5x to the fourth times g plus f, which is x to the fifth, times the derivative of e to the negative x. You have to use your chain rule, so that's going to be a negative e to the negative x. So I'm going to clean this up a little bit. So this is equivalent to 5x to the fourth over e to the x plus x to the fifth. I should say negative x to the fifth over e to the x. I can condense this to a single fraction, which would give me 5x to the fourth minus x to the fifth all over e to the x. So now when you're trying to figure out, again, you're doing your comparison to 0, again, I'm going to factor the numerator. So f prime of x is equal, I can take out that x to the fourth. That's going to leave me with a 5 minus x all over e to the x. Again, remember, I need to know, no matter what, I know this denominator is going to be positive. Again, remember, I'm doing a comparison to 0 for the derivative test. So now I know that this, no matter what value I plug in for n, anything to the even power is going to be positive. So the question is what's happening inside the parentheses. Starting with 1, 2, 3, 4, all of this is going to be greater than 0. Now when I plug in a 5, this is going to give me something equal to 0. But starting when I plug in 6 for n, 5 minus 6 is going to be negative, 5 minus 7 will be negative, 5 minus 8 will be, so this is going to be less than 0. So this is going to become strictly decreasing. Again, remember, at n is equal to 5, it becomes 0. So this is going to become strictly decreasing. These values are going to become negative for your n values that are greater than or equal to 6. So at the sixth term, this is where the sequence will become strictly decreasing. So it's strictly decreasing for your n values greater than or equal to 6.